Hello, this is Dr. Liu. In this video, we'll explain how to add vectors graphically. So just imagine you have this treasure map. So you start from here, and you want to reach your treasure. So the treasure map tells you to go in a certain direction. Go to the east, 15 paces. Okay. And go north 10 paces. Okay. And then go, say, southwest, a certain amount of paces. And then dig. Okay, so you dig here and you get your treasure. So this basically involves a number of steps. You're moving in certain direction, certain lengths. So remember, when we introduced vectors, this is the properties. There is a magnitude, how far you go, and also direction, which way you're going, right? And then by concatenating them together or doing a composition of several vectors, you're probably better off if you just went this way. If you read the whole treasure map and somehow mapped out where you will end up, you don't have to necessarily go through these steps. Let's just assume that there's no obstacle for you to directly go, right? Sometimes you could. So there are a lot of times we need to add vectors, not necessarily just to get to our treasures, but to do things such as adding velocities. So I'll give you an example. Say if you have a car, so here's a car. So car 1. Alright, so let's make it more car-like. Okay, and here's another car, there's a car 2. And the car 1 is going at a certain velocity on the highway, and car 2 is going at a slightly higher velocity. So you don't really know car 2's exact velocity because you don't ride on car 2. You're here. You're riding on car 1. Okay, so it's like a ride. It's not like an amusement park ride. Okay, so you know your velocity v1, and you observe this other car. So you find out how fast this car is, how much faster it is compared to you. So there's this small quantity of relative velocity, car 2 versus 1. And that's how you observed it. You saw it, and you saw it probably pulled away at, say, 5 miles per hour faster than your car, which is maybe 55 miles per hour. So you add the two together to get this exact one, the V2, because V2 is equal to V1 plus this V21. So your 55 miles per hour plus their 5 miles per hour faster than yours, that gets you their velocity. And these could also be vectors. It's pretty easy in 1D because you can normally do this in your head. How fast you are, how fast you think the other car is faster, and you add them together. What if this is different? Say this is a top view now. Okay, we can't really see the wheels, but we can kind of see them. So here we have a sedan. Okay, I think I'm improving on my drawing skills. So it is going forward, so this way. On the other hand, there's also this overhead bridge, and there's another vehicle right here. It's also going. It doesn't really go along the same direction. It's more or less cross direction. Okay, so could be a pickup truck. Okay, so a pickup truck was this truck bad. Maybe it's empty. All right, so it's going this way. So this is the V1 vector. This is V2 vector. So what is V2's velocity relative to V1? So if you're riding along car 1's driver, what is this other vehicle doing? You know that you have this bridge, so you know, yeah, this truck is driving along the bridge. It's it's perpendicular to which way you're going. It's just overhead. It's easy, right? What if you remove everything? Say you remove the road, you remove the bridge, and somehow the vehicles are still going. Maybe it's in outer space. These are two spaceships. So it'll be really confusing what the other vehicle is doing or other spaceship is doing. And plus, it would require us to add vectors or even subtract vectors. So I would just do this. So this is V1, and the v2 is this way, so v1 plus this v21 has to be equal to this v2. Okay, so this could be the v2 versus 1, and okay, versus 1, and then this somehow results in this v2. So this already starts to look pretty confusing. We should get started with how to add vectors with a formal introduction, because this 1D doesn't work anymore, right? We need to deal with full 2D. So how do we add vectors? We know that we can have these vectors such as a and b. So let me get a vector a, and it has its ax and ay components, right? It also can be represented as an a magnitude and an angle of a with respect to the x-axis. We also have a vector b. B has the same property, bx, by, and it could be described as b and the angle b with the x-axis. Okay, so how do we add them? Let me just draw something that represents a. So this is a, and maybe this is b. Okay, so how to add them? Well, here's how to graphically add them. So this end is the tail of a vector. This end is the tip. It's a vector is like an arrow that you can shoot out of a bow. So this is the arrow side. That's the tail, the feathery tail. So this is also, it's B's tail and B's tip. So to add the two together, we use this rule. It's called tip to tail. It doesn't really matter which one's tip to which one's tail. So here's a plus b, both as vectors, and I'll try to do my best to replicate a. Now I realize I can exactly replicate a because I'm drawing digitally. I can just take my time, right? Just make a copy, and I'll paste a right here. Okay, so now it's a. Exactly replicated. That's better than what I can do on the whiteboard. So let's also replicate b. Okay, so let's copy that, and we'll paste it. So here what I'm doing here is take b and put b's tail at a's tip. Okay, so that's good enough. So the tip of a touches b's tail, or you chain them together, tip to tail. So the sum, let me use a ruler to guide me to draw this line, is tip to tail, this tip and this tail. So, okay, I hope this is good enough. It's different. Okay, can I maybe change the color even? I don't think I changed color here. That's okay. I use a different pen. Okay, so right here. So this is a plus b. Okay, so the way that we did it, let's switch back to black. This is a, this is b. So we chained a and b tip to tail, tip and tail. And then there's this one free tail that hasn't been changed to anything, this one free tip, so we just draw across, and this is our a plus b. We also call this our resultant. So this a plus b is this resultant vector r. So this is r. Okay. Another way to add AB is to put, this is A's tip chaining B's tail. What if you just swap them? A's tail chaining B's tip, that should be the same, right? Because A plus B, we're experienced with that. A plus B is the same as B plus A. So let's prove that. So A plus B equals B plus A. Alright, so in order for us to make better use of our time, I'm going to use a the vector simulation right here. All right, so we have A here. So here's an A, and here's a B. They don't look the same, and let's try to replicate what we have under. Let's see. Okay, so we have B like that. So okay, let's see. Alright, so this B here looks somewhat like this. Let's see how close we got it. A bit more vertical, this is a bit more horizontal. Okay, so we chain them together, and I can just tap this sum here, and this is the sum, A plus B, right? And you can also just move them around. See, the sum can stay, and I can move this over here, move this over here. So now B's tip changed with A's tail, right? So this way is like the bottom left and the top left gets you this same thing as if you move A over here, have A's tip change B's tail, and this is like the bottom right and top right. They still get you the same thing, the same diagonal, right? So I wish I could display them both simultaneously, but this simulation doesn't allow me to do it. So what I could do is I could make a screenshot, and then I'll make another screenshot. So I'll put the two screenshots next to each other. Alright, so let's do this. Okay, so we'll just paste this here. I'll use my mouse to move it. So this is one way to add A with B. And then I'll just move this over here. Take another screenshot. Okay, so now we can see that you can basically have the same diagonal for this this parallelogram, right? So that's how these two are equal to each other. This is A plus B, right? This is B plus A. So these two are equal to each other. So if I just sketch something quickly here, here's A, here's B, B again, A again, right? This is A plus B. That's equal to this diagonal. Well, that didn't do that too well. This is the R resultant. Or you can move B here and A here. So tip to tail again adds to that. So this is just either you're talking about this side, or you're talking about this side. They're basically sharing a diagonal, so they add to the same exact sum. Okay, so let's play with that simulation a bit more. Okay, so now what we want to do is we want to see how the sum will react to these two vectors, because we have some experience with summing scalars, adding numbers. We don't have a lot of experience with adding vectors. So let's try this. First, let's see how A and B's magnitude will affect the sum. So apparently, the longer these vectors are, the bigger the sum seems to be. But what about their respective angles? Okay, so the angle between A and B, if I try to make them as parallel as possible, see that sum is exactly here. If A and B are parallel to each other, the sum is just like a scalar sum. Just add the two quantities magnitudes together, and the direction doesn't change because you just keep going the same direction along B as you were going along A. But as they start to diverge into different directions, you can see the sum start to get shorter, and the sum could even be shorter than this A. See that the sum is not as long as A anymore, or even shorter than the B. So the sum is basically could be smaller than either A or B. It could also be 0. Oh, I see. That actually also defines the negative of a vector. And if you add your negative, you get 0, right? So it's like 5 plus the negative 5 is 0. So if you add your negative vector, you get 0. And here we have no sum. That's why this is B is exactly the negative of A. So how do you get negative? Well, you have the arrow pointing in the opposite direction. You don't change the line. You don't change the length. You just switch the head and the tail. And then you have this negative going on. All right. So that was negative. And we also experienced that the sum can be as long as the two magnitudes added together, but that only works if you have A and B exactly in the same direction. I'm trying to get to that point. Okay, same direction, right? So when A and B are parallel, the sum is as big as A's magnitude plus B's magnitude. But if you don't have that special condition, the sum is less than these two added together because you're like going a long way, right? This is a direct route, so the sum is shorter than if you had to take a long way. Everybody understands that, but once you get to your mathematics, you may forget it. So remember, the sum's magnitude could be anywhere between 0 and the sum of each magnitude, depending on the relative angle, right? So let's manage this. We'll just do one more thing that we just learned that this is what we have A and to negative A. So this is A. Oh, that's not parallel enough. That still isn't. Okay. So this is negative A. Essentially, you're just switching which one's tail, which one's tip. So then you have a negative because we know that A plus the negative A is supposed to be 0. So you're just double backing. You're back where you started. Okay, so what about if I add multiple vectors together? Well, we're kind of running out of space, so let's create more space here. Okay, so now we have more space. So if we're adding more vectors together, it's still going to be the tip to tail. So something like this. If you have an A, you have a B, maybe there's also a C, there's also a D. So this is A, this is B, this is C, this is D. So you end up with this resultant. This is resultant R. Let's color it differently. Let's use a blue. So this is the resultant. Okay, I think I did okay. All right. So you're basically just going around the tip of one vector to the tail of the next, and next, and next, next. And also, as we know, you can change the order you combine these vectors because you're allowed to do that in additions, right? This is A plus B plus C plus D equals resultant. Everything's a vector. And you know that you can switch them around, say A plus C plus B plus D. They're the same as this R. So I'll have some trouble actually switching them around because this is, let's see if I can do that. So I'll just duplicate this and see how easy I can move them around. So AC BD. All right, why did I do that? Right. Okay, so this is B. Okay. And that was D. Okay, I didn't draw these arrow. Oh, I see, I did. I kind of left it down there, but that's okay. I'll pick it up. So, okay, so A plus C first. And then plus B. And by the way, D is downward, right? I still had that arrow down there. So can I, excellent. So I was a bit off because these things are hard to align. So this is that A plus C plus B plus D in a different order, but still with the same exact outcome. So we'll just say that that's this, and this is that. Alright, so we can chain them together, and apparently as I showed you, it's difficult to hand draw vectors and try to maintain any type of accuracy. I gotta use, besides graphing paper, also rulers and protractors, so it becomes a hassle to draw these vectors if you have to maintain accuracy. So in the next video, I'll explain how to do vector additions analytically, and that will give us a better idea and also how to control the exact precision you're adding. Thank you.